Okay, we're recording. So we're gonna introduce the last topic before the exam. I made a post online or sent an email out with the exam date, and the last topic will be basically covering cutouts, and it will be um, basically two sections to it. The first part I would just do online because it's more theoretical. Well, common practice what they often do in the industry, and that's based on just empirical data gathered over the centuries, or decades in this case, and how they applied those equations to it. It sounds very dumb, but a lot of times, especially in some cases with the aerospace industry, things are done because it's been done that way X number of years already. So they don't want to change it. And with that said, is the topic will be, of course, cutouts. So, like I said, first section will be, I think it's the first 20 minutes. I try to get through it pretty quickly. Will be just empirical data. It's just good to know how words come from, but it's not necessary to remember, and it will not be exam. And the second topic will be what happens if we actually take out a panel. Say, for example, what we see there is the door panel. So of course, when you take a door panel out, or panel out, say inspection hall, you will disturb the shear flows, and how do they get redistributed? And then if we have time, that will basically means next week we'll talk about how to analyze a beam in a bit of more details than just looking at the panel cutout. Because if you take out a panel, then the forces will be redistributed. We can assume that they get redistributed as shear flows in adjacent panels, or we can assume that some of the beam, the stiffeners, take up all the normal forces, and the shear and the panels will take up the shear flows. With that said, of course, as engineers, you try to avoid any cutouts, but of course, it's impossible to do so. You have to think about like doors, windows, even lightning holes. So, for example, if you look at a section of a wind box, when you have the spars, they just cut out holes out of them because the stresses are not that high. So by adding a hole in it, even though you add a stress concentration factor, you can get overall lighter structure out of it. So it's a trade-off that you make as an engineer. Yes.
I think I remember us talking about a situation where you put in a hole to simplify the shear loading or something like that to make it easier. Is there any kind of situation like that where these two situations would offset? Where a hole weakens it, but then another one can distribute the
I think you're talking about there's crack propagation. You drill a hole in it so that it doesn't.
Yeah, that's different. So in that case, what you're trying to do is to stop the crack from propagating. So basically, if you have any crack propagation, say you have a panel, and there's a cutout here in the middle, so the stress concentration will be the highest on the sides. You have an uniaxial loading, so basically you create a crack propagation near the side of the panel. Let me actually go, make sure I switch cameras. So, yeah. So here's where you start your crack propagation. If you analyze this, it'll be something like this, and you can analyze the crack as an opening. So what you then do is, since this is basically cyclic loading, this will close, open, close, and the crack will propagate through the structure. So what you do is you basically cut a hole here at this pin, at this location. So what you actually do, even though you increase the hole, the overall KT factor, stress concentration, can go down. So you should postpone a bit more of the crack propagation. And of course, on material or on a molecular or grain level, what you can also do is by changing it, you can actually locally harden it by just straining it in a certain way. So then also becomes a bit more difficult from the crack to propagate. So that's totally different than what we're talking about here. So here what we're talking about is having a panel which is pristine, and then say we have a couple of stiffness and strainers going through it, so they take up the normal forces, and we have a panel which basically has the shear flows. So again, in the panel, so if we calculate the shear flow, they have to be in equilibrium within the panel itself. So if we now remove this, what we basically can do is we can say, well, this is our pristine case. Let's see if I do it like this. So we have our pristine case where all the panels are existing, and then we basically have our pristine case, and we take whatever this panel is. If the shear flows are going in this direction, we basically add an opposite equal shear flow to it. So when you add these two together, we get our panel width cutout. So they cancel each other in the middle section. But what we then have to do is you have to calculate the remaining panels, and we'll get to this later in this lecture, hopefully. And you basically calculate what the effects of this transverse or the flipping of this shear flow on these sections, and then you add them to these sections and to get your final result. That's basically what the topic will be for this day. Okay, so like I said, of course, when you create a cutout, you have a couple of choices. We can go for circular, which is easy. We can go for rectangle sections. So for example, in some cases, we are also limited into what we can choose. For example, door is never going to be an elliptical door. It needs to be have enough space to people go in and out. So you go for rectangle with cornered sides in order to reduce the stress concentration. But every type of cutout will create its own stress concentration. And we can see, for example, in this case, the elliptical will be the best. Has a low stress concentration at a value of 2.3 at the maximum. So basically, you multiply the stresses at those points by 2.3. And even though a circular is better and elliptical is better, in most cases we have to go for a rectangular case. And of course, this is all for metallic, so keep that in mind. When you go to composite, tins becomes way more complicated, but also at the same time, tins can become simpler because composites have a better fatigue life resistance than metallic structures. Some composites.
Is there any reason why you go with the rectangular?
Sorry?
Is there any reason why you go with the rectangular ones despite that the circular?
Yeah, because you optimize the space. So yes, the circular gives you an easier, less stress concentration, but if you make a door out of it, going in and out is just that space, because you have to think about it. The sides of those, the section where the people go through will be basically the middle section of a circular, so the sides of it.
No, but let's see the windows of the thing.
So why the windows are elliptical. So yeah, the window section that you see is looks very rectangular, but it's in fact actually elliptical. And again, it has to do with the fact what the consumer wants. We want windows, we want to look outside, so they've catered to that as well. So we see with the new 787 and the A350 from Airbus, the windows are significantly larger. You will notice that if you walk into those aircraft immediately. And the reason for that is because they use composites for the fuselage, you have lower fatigue cycles, or they fatigue less, so you can actually enlarge in the windows and still be within the bonds of the stresses that you need. So, but most commonly, regardless of what type of window you do, what type of cutout you do, you have to reinforce it. You cannot just leave it open as is. Stress concentration will rise, so you have to basically take into account that those stress concentration will be high at those locations, and you have to come up with certain, circular reinforcements to cope with the stresses in those cases. And there are a couple of things you can do. You can basically add a doubler to it. So basically just a circular ring around the cross section that you rivet to the panel or in some cases adhesively bond. And that will basically add some extra material to take up the additional stresses and make sure that you have basically a better load pad that can handle the additional stresses due to the stress concentrations. And simple stuff like just bending the flanges based on empirical data, and especially in the 70s, 60s, 60s, 70s, and 80s, when a lot of research was done on these things, it's based on empirical data. So they saw that if you just bend the edges from the cutouts, you see a reduction in stress concentration. You can go thinner, therefore lighter. So, and often what they do is they basically have tables like this. So you can find these in the literature. And basically it's very well defined what you can do. So if you have a diameter hole of say 2 inches, 6 inches, or whatever it is that you want to do, based on that you can figure out what the flange length needs to be in order to minimize the stresses. Given there's a 45-degree angle, again, that's empirically determined to be the best angle. So a lot of times when you go ahead and design these things, especially for lightning holes, these are like sections in the wind box where your stiffeners and strainers are going through. So you want to create, and in the spar you want to basically lighten it, slim it down a bit the weight. So you create these holes to it. And these holes are not that big, and because of that and how much stresses they see are somewhat lower than what you will see in a window. You can do without reinforcement. You can just basically do with making sure that the end of the cutout is basically bent at a 45-degree angle and a certain length to it in order to cope with extra stresses. And of course, what they also have to do is you basically go through a checkmark box from all the different things that can play a role. Of course, the diameter hole plays a role, the height of the total spar, because the hole cannot exceed a certain ratio, all plays a role, and basically it's an empirical data that you basically look at different graphs that's been developed over the years, and you basically see and you check where your design falls in within those graphs. Based on those graphs, you can determine what the hole size is, what the height of your or if the height is fixed, what the maximum hole size is, and if the hole size is fixed, then you can determine what the max or minimum height of your spar can be. And of course, thickness will also play a role, which thickness you need. So a lot of things are very well defined, and you have to maintain or you have to meet all the criteria in order to have a successful design. And this is just for unreinforced cutouts. And this is an example of the graphs that you can literally find in the literature. I think NASA has a bunch of reports out when they developed all these graphs and did all these experiments. And you can see that the most used aluminums, 7075 and 2024, already also shown. The results are shown for those two materials. Okay. And then you can also see how the stress concentration affects your shear flow, and based on your shear flow, how the net shear stress. In this case, they use F, which is I maintain the same variables they use in the NASA report. So normally we start for it, but how the shear stress between the holes and between the hole on top and bottom vary based on the hole diameter, the height, and the thickness. And of course, if you have riveted cutouts, you have to take into account the stress concentration on a rivet. So again, same procedure that you have to apply over and over again. I'll go through this a bit faster than I normally would, because I want to focus on what we go into the shear flows ourselves. Again, you can do a small example. It's already down for you. What basically comes down to, again, just looking at the data that is available, the graphs, seeing where your design falls in between. So what is my thickness, what is my diameter, I think in this case, and what's our shear flow. So you've given a material, thickness is given, and the question is to determine the diameter and the spacing. So basically you have two variables, and then you basically plug in the numbers that you already have. You identify which formulas that you can that we've shown previously you can use to determine the ratio of diameter and spacing. And it's nothing more than just following the given data and equations in the literature. And that's how you would basically define an unreinforced cutout. It's very lame, but this procedure is still being used up to date, especially in like smaller aircraft. If you think about Cessna, even the Gulfstream G650, engineers use these kind of first order assumptions in order to come up very close with your design or your, say, second stage after the preliminary design, when you go into your detailed design. And at the end of the day, everything is being validated either by a full numerical simulation, and then at the end of the day, also validated using an iron burr test, where you basically have everything and you just break it, you bond strain gauges everywhere, and you can see if your experimental stresses are within range of what you predicted. If so, it's good. If not, then you basically go back to the drawing board. So what do you do for every aircraft actually? So the first piece, first manufactured aircraft has always been broken. So normally you will have your aircraft somewhere located and you have your wings, and basically they lift the wings using huge pulleys and huge machinery, and they lift it up until it basically breaks. And the idea is that you lift it up to ultimate load, so sigma ultimate, or the force that corresponds to sigma ultimate. Then your structure must be for 3 seconds holding, and after 3 seconds it may fail. So, but if it fails at, say, 2.958 or 998, that means you failed your test. So you have to redraw, go back to your analysis, see where the first failure occurred, which section it is, say halfway to win, for example, and you have to redesign that section. Or you need to come up why it failed. Maybe everything was fine, but just before the test, somebody dropped a hammer on it and there was damage there. It can be simple as that. But you have to hold the 3-second rule. So,
What's with the 3 seconds? What's with the 3 seconds?
it's in order to verify that you can hold the ultimate stress. So you go low to ultimate stress, you hold it, and then they verify, okay, it can handle ultimate stress or ultimate force as the once in a lifetime force that an aircraft can see. So, and often any good design, a perfect design would basically fail it after 3.1 seconds. But often we see that those aircraft are way over designed, so they will fail after, say, way above 20% above ultimate or something like that, or 10% above ultimate. But again, so everything at that stage, everything has been recorded. That can be helped to evaluate your numerical analysis and your design steps down the pipeline. Again, so we discussed, going back to the reinforcements. So we discussed unreinforced cutouts, where they basically just bended the flanges. So we can also have beaded flanges, which basically has a curvature to it, as you can see here. Again, based on experimental data and just trial and error, they see that this will have advantages over in certain sections of the aircraft over just bended flange. However, then the design requirements come also in play. Some, if you want to do the analysis on this, slightly different. For these holes, the diameter can be increased from 6 inches to approximately 10 inches, and then your angle of which you beat, your flanges bend, can vary as well. And then you basically do it again, experimental data gathering. So you test all different sizes and angles, and then you capture all that data again into a graph, and then you can use that to to determine where your design lays. Again, experimental data, empirical data based on the thickness, the width, and the radius. And then you can, if you have those kind of beaded flanges, you can again do a simple analysis on it, and you can determine what the given thickness, spacing, and diameter can be for a given geometry and loading condition. And as to do again, like I said earlier, you basically go to your graphs, you go to your equations, you can see where your data lies in between, and based on that, you decide a certain lighting hole. And the next important step is when you go into reinforcements. So we basically add riveted sections to it, a donut, or additional material around the hole. So the equations change a bit. So if you use an L stiffener or a different type of stiffener, everything changes. And what you basically do is you take into account the area of the L stiffeners into your analysis. And it's a first order analysis, so it gives you a rough estimate, but it's, in most cases sufficient for your preliminary design of your aircraft. So we see that, for example, in this case, IO is your moment of inertia, changes a bit based on the stiffeners width and length and thickness and your plate thickness. And based on that, you can again determine what the maximum width can be for a given thickness, or what for a given thickness of what the thickness must be for a given width length, or flange length and width. Again, it comes down to a lot of empirical data, determining where your design lies in, and which region it lies, which graph you have to look at. These graphs are given for, I think these are like the ratios of diameter over the height. So if you have a certain ratio, you know approximately what, based on the ratio and your thickness here in the bottom, you can determine what your stress concentration is, and then you can reuse that stress concentration to determine what your reduction factor is and what your corresponding shear forces are in the segment. And based on that, again, a lot of empirical data, but you can design your structure with it. And then, of course, once you design your structure, then you can check if the rivets can match. So if you have a certain web thickness not determined, then you can check using again, empirical data what type of rivets you may or may not use. Again, a small example, we can skip these. A bit more detailed example. But you basically go through all the steps again, what I mentioned earlier. So, this is the topic I want to focus on for the remainder of the lecture. I'll go to the, and that's what I'm basically dealing with periodic cutouts. So instead of focusing on, let's go to the lectures. Okay. So instead of now focusing on empirical data, I want to focus a bit more on what can we do ourselves, what can we calculate using the equation that we already have derived in the previous segments. So like I said, the previous slides, if you have time, I'll go through them again yourself, because it's pretty valuable to know how these things are came up with, and that a lot of things are designed based on empirical and data from even as old as the 50s in some cases. But for our analysis, we're going to focus on two types of cutouts, periodic cutouts and non-periodic cutouts. And in case for periodic cutouts, we will investigate basically both in the longitudinal direction and in the circumference. And for non-periodic, that would be just a single cutout somewhere in your panel. So what we assume is that regardless what type of cutout we have, is that we have given the far field shear flow distribution. So we assume that far away from our cutouts, the shear flow that we have given is a certain given factor. So let's do periodic, and then both in, we see the longitudinal and circumference direction. So let's draw this. Then this will be basically our panel. So we assume that the shear forces or the shear flows given at this location will be, say, a certain Q. Let's see in the right direction. So this is Q, and we have some far field Q here as well, and we'll have far field Q and another far field Q here as well. Now we can define a couple of different parameters, and we also assume that this is, for example, a cutout, so there's no panel here, and because it's periodic in both longitudinal directions, so in the X direction there's a cutout here, and there's a cutout here, and we assume the same thing is repeating, so the number of panels is continuously repeating. So what we assume is the following. Let's call this D1, this segment is D2, and this total segment is just D. Similar here, we have okay here, so this is L1, L2, and this segment is L in total.
Is there any difference between D2 and L2 and DW and
It can be. It can be. So it's basically as long as they. So now we use L1 or L2. What do you mean in the lecture slides that you use D? Oh, you know, it doesn't matter. So I think in the lecture slide I go for DW, right? Yeah, and LW.
so it doesn't make a difference?
No,
Okay.
it's just a value. I can stick to DW and LW as well. So we have some average shear flows given at the ends, and we have some geometry given here. And then the idea is determine the shear flows and the surrounding panels around our cutouts. And we're going to focus on this 3x3 grid for now only. So let's define that. I think this is Q1, and then what we have here is Q3, and this one is Q2. And in a similar manner, we have Q3 here, and Q1 here. Double check if I wrote this all correctly. This is is Q3, this is Q2, and this is Q1. No, that's Q3, and that's Q2. Yeah. So what we have given is basically we have Q average as a far field, and we basically have to determine Q1, Q2, and Q3 given a cutout. And what we do is, it seems complex, but it comes down to equilibrium of forces. Forces in X and forces in Y. So the first equilibrium what we do is, we know that we have an average Q given here, Q average. So we say, well, we're gonna do an equation of the forces if we basically would cut out or investigate the panel along this cross section. So let's call this, I think this and second one's, yeah. So this is second place, and the first place will be equilibrium of equations around through the cutout section. So we can determine what the shear flow will be at that segment. And we focus, because since it's periodic in both X and Y, we can just have to focus on these two panels here and these two panels. So basically even limit ourselves into a 2x2 panel, because the rest what we can assume is being repeated somewhere else. So when we solve this, the rest will fill in, because it's a repeat. Imagine that this is similar as this panel, or here you would have a cutout, so this will be representative of this as well. So you can always find, this patch of 4 panels, you can place anywhere on structure because it's doubly periodic. And then we just take the equilibrium equations. And we can say that, for example, in this case, so let's redraw that. Let me see. Okay. So if you redraw our figure, we'll have one panel here and basically 2 panels there, and this will be our cutout. And this is our Q1, and this is Q3, and this is Q2. So these arrows indicate how the shear flow goes. You can basically say within the panel, the arrows are pointing basically upper right corner. So this is basically a simplification of doing 2 of these arrows. And of course, if they would be in the opposite direction, then the arrows will be opposite. Okay, so this is just a simplification I do. So basically we said we take the equilibrium equation, so we said we're going to take it halfway to cutout. So this is Q1. And we look at the equilibrium equation in that direction. So we know that this length was L1, and this is LW, and we know that this is D1, and this is W. So if you take the equilibrium equation in this case, what we'll see is summation of forces in X. What we get is that Q1 times L1 must be equal to Q2 times LW plus Q3 times L1. So basically, if you would make a free body diagram out of this, what you will get is this is our say panel 1, so this is Q3 acting in the X direction, this is Q2 acting in the X direction, and on this segment, Q1 is acting. Okay. Does everybody get this step?
So that's just the line that
Yeah.
runs from Q2.
Yeah.
Okay,
So basically just at this location.
got it.
So then you can say, we know when we do an equilibrium forces, we multiply shear flow by distance to get a shear force. So we multiply Q1 by L1 and Q2 by LW, because these two are acting to the left. They're basically negative. So this will be Q1 L1 minus Q2 LW minus Q3 L1 is equal to 0. So then you take it to the other side and you get this following equation. Yep. And you can repeat the same thing, but then say on the top side, where you basically have Q3, Q2, and this is the segment, and on the top side you have the average shear flow, which was the far field shear flow. And you can repeat the same thing. So we now did equation at location 1, basically, summation of forces, and then we do the summation of forces at location 2, somewhere far away from our shear flow, from our cutout. Say at the segment where we have our average shear flow again. And we can repeat the same thing, and in this case what we get is that Q3, that was L1, plus Q2 LW is equal to Q average, in this case L1 plus LW, which is the same as Q average times L. Because here we define L being the sum of Q L1 and L average. Okay, so if we now collect our variables and our equations, we have 1, 2 equations, and we have 1, 2, 3 unknowns. So, and again, we need an additional equation in order to solve this problem. Keep in mind that the panel dimensions are given, and the shear flow, the average shear flow, is also given. So Q average is given. So basically we have to come up with an additional equation. So we look again at our problem, what we have. We know it's periodic in both in X and Y. So we basically investigated what happens if we take a cutout at a segment along X. And keep in mind there's basically only 2 locations because it's periodic in X and Y, and how we drew it, how the problem is run. This cell we said will repeat here, will repeat there, will repeat there, etc. across the cross section. So basically already examined all the possible locations that we can do in equilibrium force in the X direction. So the next one, in order to come up with a third equation in order to solve this, we must look somewhere at the vertical direction. In this case, we can basically look at either, again, similar thing, through the cutout or just far away from the cutout. In this case, we go for through the cutout. And that's basically, if you do both, we'll give you the solution, but one will be just a bit easier. So if you do the summation of forces in the Y direction, and let's call that, let's see, tree. What we get is we only have to deal with Q2, and we have to deal with let's see. Now we do it here because then we know what our average shear flow on this side is. So So we will have only Q2 because this cell is again Q2, Q2. We have our average shear flow acting on that far side. So what we get is that we multiply Q2. Let's draw this force as well. So we get shear force like this. So we get Q2 times D1 must be equal to the average shear flow because this is an empty cell times D1 as well. No, times D. Yeah, Q average times D. So let's draw that a bit. Maybe we can use this as well. So we have Q1 times D, and we know that somewhere here, far away, acts our average shear flow, Q average. So we can do the summation of forces basically around this panel. So we have Q2 times D1 must be equal as Q average times D1 plus DW, which is D. What this gives us is basically a third equation. So now we can solve our problem because now we have 3 equations and 3 unknowns. Let's basically rewrite this. Let's see. Yeah. I'll rewrite the equations and then we can start solving them. So we had Q1 L1 is equal to Q2 LW plus Q3 L1. We had given Q2 LW plus Q3 L1 is equal to Q average times L. And we had given Q2 times D1 is equal to Q average times D. So in this case we have 3 equations, 3 unknowns, so we can solve it. Now if you solve them, what you will get is Q1 is equal to Q average L over L1, and then you can basically rewrite that to Q L1 plus LW plus L1 over L1, which is equal to Q average of 1 plus LW over L1. Q2 is equal to Q average D over D1. You can rewrite this in a similar manner. So average over DW plus D1 over D is Q average 1 plus DW over D1. And Q3 is equal to Q average L1 over L over L1 minus D over D1 multiplied by D or LW over L1. And this can be simplified to Q average 1 minus DW D1 LW over L1. And there's a very simple reason why I don't do all the steps, because I always mess up somewhere. I basically did use model up. But now you have basically, if you have a 2 periodic cutouts, we know what the shear flow distribution is in each of the panels, because we can reuse these equations to determine what the shear flow is based on our given cutout. And shear flow given it away from the cutout section.
So this is Q equals Q average DW plus D1 over D1?
Which one? This one?
Oh yeah.
Yeah, DW plus D1 over D1. So now then you can do DW plus DW over D1 plus D1 over D1, so you get 1 over. Basically what you do is, so this one is very straightforward, right? Because Q average is given, so Q2 is determined very easily. So you get Q1, Q2 is equal to Q average over multiplied by D over D1, and then you plug in what the value for D is. And what you then do is you can back substitute that value into, let me see, this equation or the Q3, and then you substitute Q1, Q2, and Q3 into this equation to get Q1. Like I said, it's a bit of tricky, and I have to mislabel one of the L1s or D1s. So what we can do is, so this is basically valid for when we have the periodic cutouts both in longitudinal direction and in the vertical direction, circumference direction. But again, that's a very special case. What we can do is also assume that we only have periodic cutouts in the vertical section, but not in the longitudinal direction, or on the longitudinal direction, but not in the circumference direction. And what it basically does is, it changes one of our equilibrium equations that we started off with. So I think, yeah. So if you remember this correctly, we had our equilibrium equation number 3 was Q2 times D1 is equal to average Q multiplied by D. And that equation will basically be changed because our repeating cell is no longer these two segments, these 2 by 2, but it will be whatever this cell is. If this is 3, let's assume this 3 cell segment, because it no longer repeats in X, Y, and Z, so at least in Y direction, we have to take the equilibrium equation, this whole segment into account. For now, we just assume, let's assume a 3 cell section. So our equilibrium equation in the vertical direction changes. Now we have basically something like this. Cutout and another cell. Say this is our repeating our cell in the Y direction, and this keeps repeating every single time. So now what we have is the average on this side, and we get 2Q2s on this right hand side. So if we rewrite that equation, we'll get us Q2 times D1 plus Q2 times D1, so we get 2 Q2 times D1 is equal to, in this case, D1 Q average multiplied by D1 dW plus D1. So we get 2D1 plus dW. We get 2Q1 D1 is equal to Q average 2D1 plus dW. And our equations in the horizontal direction, because we still have the periodicity in the horizontal direction, in the longitudinal direction, they remain the same. So basically what we get is that equation, called this 1, 2, and 3. 3 gets substituted now by our new equation, that is 2 times Q2 times D1, and this is 2D1 plus dW. Now what happens is we again have 3 equations and 3 unknowns, so we can now can solve for this equation as well, for this problem. So we can do that as well. In this case, if we solve this system of equations for Q1, Q2, and Q3, what we get is that Q average of Q1 is equal to Q average 1 plus L1 over LW, and Q average is 1 plus dW over 2 D1, and Q average is equal to 1 minus dw 2d1 lw over L1. So we had x xy. Let's get those equations out again. Average. This was 1 plus L1 over LW. Average. Okay, average. 1 minus. Double check. This is perfect. So what we see is that if we have periodicity only in the longitudinal direction, we get our shear flows as a function of our average shear flow. So Q1 is the average shear flow multiplied by 1 plus L1 over LW. And if we have periodicity in both longitudinal direction and circumference direction, we see that Q1 remains the same. Q2 and Q3, they change, however. And we see that in this case, Q2 average. So Q2 we had here over D1, here we are over 2D1, so this basically becomes less. So our average shear flow, or our shear flow in Q2 decreases. At the same time, we had here D1 and here we had D2, but we have a minus sign, so the shear flow in Q3 increases. So what we can see is that the effects of our cutouts, depending if we have a cutout only in X, or periodicity in only in the longitudinal direction in X, or we have periodicity in both longitudinal and circumferential direction, so both in X and Y, will have its effects on our shear flows in the panels around the cutout. So Q1, Q2, and Q3. And of course, that effect needs to be quantified. So this is basically a very simple equation that we have derived and could be used in every time that we have a periodic cutout. So as long as we know what our far field stresses are, we can determine very quickly what our cutouts are around our cross section, or our cutout, what our shear flows are in the panels adjacent to the cutout. So this is again a very straightforward and simple exercise. Yes.
Q average is just the average of all the four corners or something?
No, Q average is the far field shear flow. So you have to think about cutout. Say let's do this most simple case. A plate with a hole. So you load this with a certain sigma. Right? So this is our applied sigma stresses. But if you then look at a cutout, so here you will have a stress concentration that is basically 3 at this edge. So the applied load is 3 times as high as your far field load. So, and if this plate is long enough and wide enough, what you will see that after a certain point, say this is our plate, this is our hole. So yes, we had here 3. At one point, it basically dies out, and at this location, the stresses are still our applied stress. So far away from our hole, the material does not see an effect of that hole presence. And that's what we mean with our average shear flow, far field shear flow. So far away from our cutout, we have a given average shear flow. But as we move closer to our cutout, or in this case the hole, we see that the shear flow or the stresses are affected by the presence of the hole because they have to be redirected, etc. I think we have 5 more minutes. Let's see. Yeah, let's remain. Yeah, I'm gonna go to the lecture slides so we can basically finalize the cutouts in the last 5 minutes that we have. So this is what we discussed. We discussed first periodic cutouts in both X and Y, and we derived the equations and how the shear flow is affected in the panels adjacent to our cutout. Yeah, and to do so, we basically said we are looking at the equilibrium of forces in both direction of periodicity. So we look at first the horizontal equilibrium forces, and we look at the 2 locations, one through the cutout and one away from the cutout to our, say, on disturbed panels. And if we look at the shear flow, the equilibrium of shear forces, what we do is we multiply the shear flow by the length, and we just get the shear force, and then we can do the equilibrium forces. And if we did this in X, it gave us basically 2 equations, 3 unknowns. So we basically have to determine an additional equation. And for that, we did a cutout on the vertical side as well. And based on that, we had 3 equations, 3 unknowns, and so we could solve it. And we did that for periodicity when we have only a cutout repeated longitudinal direction, but not circumference direction. And then we saw that our shear for vertical equilibrium equation changed to Q2 times 2d1 equal to Q average times 2d1 plus dw, and that affected our redistribution of our shear flows in panels 1, 2, and 3. And a quick comparison said that Q1 remained the same, Q2 was smaller, and Q3 is larger. But in most cases, what we'll see is actually that we have a cutout at a certain location. And what we do is, say for example, we want to take out the middle section here. So we have our undisturbed panel on the left hand side, and then we flip Q0 to a negative Q0 or Q, yeah. So if we add these 2 together, then our shear flow in the middle section will vanish. But then we have to recalculate what the effect is of the flipping Q0 on Q1, Q2, Q3, Q4, 5, and 6, and 7, and 8. Q7, this should just be a plus, it should not be a minus, by the way. And then we can get our actual shear flows in the panel with the singular cutout. So it's just not repeated in neither X nor Y. So that's the approach that we take. So then again, this basically forces us to determine what our Q1 to Q8 are based on our applied shear flow. And we basically do the same thing as we did earlier. We take the equilibrium of forces in X and Y through the cutout and adjacent to the cutout, and we can derive that Q2 and Q7 must be equal. Again, symmetry in this case, and they're equal to Q0, the height of the panel, say 2 plus, I think I didn't, yeah, the dimensions are missing, but assume that we have the height of each panel is Q1, H1, H2, and H3 going in from up to down, and the lengths are L1, L2, and L3. So we can get that Q0 times the height over height 1 plus height 3, and we get a value for Q4 and Q5, and then we get a value for Q1, 3, 6, and 8 all being equal, again based on symmetry. And once we have determined all the shear flows, again by just doing the equilibrium of forces in X and Y, we can determine what our total shear flow is given our undisturbed field. In this case, G0 is equal to all the shear flows here as well. So they're all equal because it's undisturbed. The shear flow, if the panels are dimensions are the same, the shear flow should be the same. And then based on this, we can just add them together, and then we get our shear flow in our cutout section. So there's a small example in the lecture sheets. I think this was slide 42. So I would recommend you doing this at home. It basically covers a situation that we have two reaction forces given and a bunch in dimensions. We basically have to determine how the shear flows basically are changed in panels 1, 2, 3, 4, 5, 6, 7, and 8, if taken into account that panel C2 is removed. So I'll recommend you doing this at home, and then if you have any questions, because this will be a topic on the exam cutouts. So if you have any questions, we can discuss that next week. So the examples worked out, so you can also double check. So the next thing I'll focus on next week is actually what do we have if only part of the panel is missing. So if you have a wind box, say on the left hand side, and we remove the bottom part of the wind box. So what happens in this situation with our shear flows, and what happens more importantly if we assume that we have stiffness and strainers that are basically located at our, say if this was a boom problem, you would have a boom here, there on the corners. So what happens and in a boom we assume that takes up all the direct forces. So what happens to the direct forces in the booms if we just also determine one of the panels is missing? So not just what happens to the shear flows adjacent to the panels, but also what happens to the normal forces in the booms. And that will be basically the last topic. I'll try to finish this in one lecture on Tuesday, and then we have the Thursday lecture basically for Q&A. I'll be here. I will go through the things that I think is important, but it will be also based on your experience. If you have any questions, email me to basically elaborate on certain topics. And if not, then I'll basically repeat the equations that are most important and some pitfalls that I've seen in the past. Okay, are there any questions?
So
No.
you say on Tuesday we're having an online lecture, or we're still gonna be in the room?
We are in the room.
Okay.
So the date after the exam, which is so the first exam will take place on the 25th to the 27th. So the 27th is definitely no lecture. The 29th, there will be an optional lecture. So if you want to reset the exam and you did bad and you want to go through it, it's basically an optional lecture. I'll be here. I'll wait till 12 o'clock. If nobody comes up, then I'll just leave. So I'll be here for you guys to address any issues and concerns. And if there's none, then you can choose to do the reset on May 2nd. Again, 48 hours. And that will be basically a course grade will hopefully be uploaded by May 7th. Okay, thank you very much, and see you next week.